Structural technology is the technology of putting parts and materials together to create supports, containers, shelters, connectors, and functional shapes. There are many different types of bridges. An arch bridge is a bridge with abutments at each end in a curved arch shape. The compression and tension are handled by the transfer of the weight of the bridge and its loads into a horizontal thrust restrained by the abutments at either side. An example of this is the stone arch bridge. A suspension bridge is a type of bridge that the deck is hung below and the compression and tension is handled by the suspension cables on vertical suspenders. An example of this is the Capilano suspension bridge. A cantilever bridge is a bridge made of cantilevers, which are structures that project horizontally into space, supported on only one end, which is how the compression and tension is handled in this bridge. An example is the Niagara Cantilever Bridge. A beam bridge is a bridge supported by an abutment at each end of the bridge deck, which is also how the compression and tension is handled within this bridge. An example of this is the Chesapeake Bay Bridge. There are 4 forces that can act on a bridge. The first one is tension, which is the act of stressing or straining. The second is compression, which is the act of compressing or being compressed. The third is torsion, which is the act of twisting or being twisted, and the fourth is shear, which is to remove by cutting or clipping. There are 3 different types of trusses. Trusses are a framework typically consisting of rafters, posts, and struts supporting a roof, bridge, or other structure. The Howe truss was designed by William Howe in 1804. It used mostly wood and was suitable for longer spans than the Pratt truss. It was one of the best designs for railroad bridges back then. When the load is centered on the bridge, the forces are much greater on the internal truss members than if the load is spread out along the top of the bridge. The Pratt truss was designed by Thomas and Caleb Pratt in 1844. It was mostly made of iron and was generally used for railway bridges. The centered load on this bridge is the main force that is applied, and it is applied on the internal members of the bridge. Also, the forces are increased on the top chord of the centered loaded bridge. The Warren truss was made by James Warren in 1848. It uses equilateral triangles to spread out the loads on the bridge. The equilateral triangles minimize the forces to only compression and tension. You can tell the difference between these 3 truss bridges because they're all designed differently so that the compression and tension is exerted differently and is put on different areas of the bridge. The 3 roadway configurations are a deck roadway, a through roadway, and a pony roadway. A deck roadway is hung below suspension cables on vertical suspenders. You can spot the differences because a deck roadway will always be hung from suspension cables and will be on a suspension bridge. A through roadway is when the road members are both above and below the roadbed. You can spot this because it has the roadbed above and below the road. A pony roadway is where the sides extend above the roadbed but are not connected. You can tell the difference because the sides will always be above the roadbed, unlike the other bridges. The process that we used when creating the bridge was that we first made a model of it onto Vectorworks. Then we transferred this model onto West Point Bridge Designer. We then were able to test where the bridge's strong and weak points were. After seeing what parts of the bridge needed to have stronger points, we went back onto Vectorworks and changed the design. The design was then drawn to scale and we printed it. Then you just had to cut the wood according to the thickness and measurements of your bridge on the paper. To test our bridges, first we weighed it in grams. Then we attached our bridge to a piece of wood connected to a metal scale. This scale was measured the load that the bridge could hold when we broke it into newtons. Then we multiplied the newtons by 10 and converted this number to grams. Then you use this number and divide it by the weight of the bridge and you get the bridge efficiency. One tip when making this bridge is to make the bottom of the bridge stronger because I learned the most force is put on the bottom of the bridge, so the efficiency would be much higher with a stronger bottom.